Redefining the core. Zero Trust is a decision system. We are here to discuss architecture, not products, not marketing, not simplified checklists. The industry has spent years debating the merits of zero trust, often getting lost in discussions about network topologies, perimeters, specific toolsets. This conversation has frequently missed the fundamental point. Zero trust is not a network design. It is not about replacing firewalls with new ones. It is not simply about moving security controls to the cloud. At its heart, a true zero trust architecture is an enterprise-scale decision engine. Its primary function is to compute and enforce trust for every access request, programmatically and continuously. This is the core thesis we will dissect today. This architectural perspective is critical. When you design zero trust as a decision system, you shift your focus from static choke points to dynamic logic. The central questions become: what information does this system need to make a trustworthy decision? How is that decision computed? Where is it enforced? And most importantly, how does it fail? This reframing forces us to think like systems engineers, focusing on data flows, state management, latency, and resilience. It moves the discussion away from perimeter-based analogies and toward a distributed model of authoritative authorization, where decisions are made based on evidence, not assumptions about network location or implicit trust. Our goal is to construct a clear mental model for this decision engine. Imagine a logical flow. Signals, fragments of evidence, enter the system. The identity of the user, health of the device, context of the request, observed behavior. The decision engine processes these disparate signals through a policy evaluation function. This is the brain of the operation, where risk is calculated and a trust decision is rendered. This decision, an explicit allow, deny or step-up authentication, is then transmitted to an enforcement point which acts upon it. This signal to decision to enforcement pathway is the foundational loop of any robust zero trust implementation. Throughout our discussion, we will treat this flow not as an abstract concept, but as a concrete architectural pattern with real-world implications. We will explore the specific data contracts required between these components, the operational constraints that govern their interaction, and the subtle failure modes that can undermine the entire system. By anchoring our analysis in this decision-centric model, we can move past the superficial vendor narratives and begin engineering systems that are secure, scalable, and operationally sound. This is not about buying zero trust. It is about building the logic that enables it, one decision at a time. The architectural mandate. Signals. Logic. Failure. This is not an introductory course. We will operate under the assumption that you are an experienced practitioner. You already understand identity and access management systems, enterprise networking, and cloud infrastructure. We will not waste time defining basic concepts like IAM, SSO, or VPCs. Instead, our focus is the architectural seams where these familiar systems intersect to form a cohesive zero-trust decision fabric. The four canonical signal classes. The decision engine is only as effective as the evidence it receives. This evidence arrives in the form of signals. We can categorize these signals into four canonical classes: identity, device, behavior, and context. The first, and most foundational, is the identity signal. This is more than just a username. It is a cryptographically verifiable assertion of who the principal is, typically delivered via a token from your identity provider. The second class of signal pertains to the device. A zero-trust model cannot implicitly trust the endpoint. We require signals that describe the device's posture and health. The third signal class is behavior. This is the most complex and dynamic of the four. Behavioral signals give a historical and real-time view of how the principal acts. Finally, we have the context signal. It captures environmental and situational parameters around the request, answering where, when, and why. Signal properties and their architectural impact. As architects, we must evaluate them based on core properties that impact our decision engine. These properties are fidelity, provenance, freshness, cost. Fidelity refers to accuracy and precision. A low-fidelity example, an IP address mapped to an entire country. A high-fidelity example, a hardware-bound cryptographic key from a device's TPM. Provenance answers, can I trust the source? Strong provenance example, an identity token signed by your corporate IDP. Weak provenance example, device health reported from an unmanaged personal device. Then there is the property of freshness. A trust decision is a snapshot in time. A device compliant yesterday is useless if compromised 5 minutes ago. Finally, consider the cost of acquiring and processing each signal. This cost is not just financial, it includes performance latency, computational overhead, and data storage. The challenge of signal fusion and integrity. Collecting individual signals is only the first step. The real architectural challenge lies in signal fusion, combining disparate streams into an actionable picture for the policy engine. One of the most common is correlation. How do you reliably correlate these signals to a single specific access request? This requires consistent identifiers across all systems. Another significant challenge, temporal discrepancies, clock skew and telemetry latency. This creates a race condition attackers can exploit. Beyond timing, signal normalization is a major hurdle. An intermediate layer, a signal normalization service, translates varied inputs into a canonical model. If required evidence is missing or untrustworthy, deny access. Policy evaluation, risk scoring, and trust calculation. At its simplest, this can be a purely rule-based model. Think of it as a series of deterministic if-then-else statements. This model is highly predictable and easy to audit. However, it is also rigid and brittle. To address this rigidity, many architectures evolve to use a weighted scoring model. Different signals are assigned a numeric weight. These individual scores are aggregated, and the total is compared against predefined thresholds. A more advanced approach involves probabilistic models. These systems build a baseline of normal behavior and calculate the probability that a given access request deviates from that baseline. In practice, most mature zero-trust architectures employ a hybrid model that combines these approaches, offering the speed of rules and the nuance of advanced models. Enforcement points. Application, API, data. The decision must be translated into action at a policy enforcement point, or PEP. True enforcement must move closer to the resource being protected. The most effective loci for enforcement are at the application, the API, and the data layer itself. Enforcement at the application layer is a powerful pattern. This involves using a sidecar proxy that intercepts all traffic destined for the application. The API gateway represents another critical enforcement locus. As enterprises decompose monolithic applications into microservices, the API becomes the new de facto perimeter. Ultimately, the most precise enforcement point is the data layer itself. This ensures that even if an application layer control is flawed or bypassed, the underlying data remains protected. The PEP must cryptographically verify the signature, and it must also check the artifact's validity period to protect against replay attacks. However, enforcement points are subject to critical failure modes. The most common failure is a bypass. Another significant failure mode is inconsistent enforcement. If these PEPs run different versions of enforcement logic, you create security gaps. One of the most pervasive and damaging misconceptions is treating zero trust as a next-generation network perimeter project. This anti-pattern continues to tie trust to network topology. Another common architectural failure is the creation of a monolithic, centralized decision engine that becomes a single point of failure and a performance bottleneck. Over-reliance on a single signal class is another frequent and dangerous failure. This creates a brittle binary trust model that is trivially easy for a sophisticated adversary to bypass. A significant architectural failure is the implementation of an opaque decision engine. This opacity transforms the zero-trust engine from a source of clarity into a source of noise. Let us now synthesize our discussion into a coherent reference model. A correct zero-trust architecture is not a single monolithic entity, but a distributed and resilient system of systems. They are not centralized in a way that creates a single point of failure. These decision points are fed by a well-defined signal ingestion bus. The bus standardizes and authenticates signals, preventing signal spoofing at the front door. The policy evaluation logic must be deterministic and observable. Every decision must be explainable. Generate a detailed decision artifact, creating a verifiable, auditable chain of trust. Enforcement is decentralized, consistent, and pushed close to the resource. This decouples data plane enforcement from control plane distribution, enhancing resilience. The system is designed for observability and feedback. Every PEP continuously sends telemetry back. This is a closed-loop system. Past outcomes become inputs for future ones. A zero-trust architecture fundamentally alters the landscape for security operations and incident response teams. The primary need for a security operations center is real-time telemetry alignment. This requires a seamless pivot from the alert in the SIEM directly into the detailed, explainable audit trails of the decision engine. For incident response teams, the decision engine becomes a critical tool for both containment and investigation. This capability transforms containment from a manual, multi-system scramble to a precise, centralized action. Red teams should be tasked with specifically targeting the zero-trust fabric. The results of these tests provide invaluable feedback for refining policy logic and identifying architectural weaknesses. We have dissected the zero-trust architecture, not as a product or a network topology, but as a distributed decision engine. Our journey has consistently led back to a single unifying principle. Trust is a computational outcome, not an environmental assumption. You must now return to your own environments and ask, where does our architecture actually compute trust? Is it an implicit byproduct of network location, or is it an explicit, evidence-based decision? The mandate for architects is to treat zero trust as an orchestrated system for authoritative authorization. This requires a deliberate focus on designing for signal quality over signal quantity. This system must be engineered for resilient decision distribution, moving away from fragile, monolithic bottlenecks and toward a federated model that can survive component failures. Our discussion concludes where it began, with a challenge to conventional thinking. The core of this self-interrogation is to follow the decision. Trace the path of an access request from end to end. Identify the exact point where the allow or deny judgment is made. Examine the evidence used for that judgment. If you find that policy logic and enforcement actions are all muddled together, your first step is to redesign those boundaries. Decouple the act of deciding from the act of enforcing. It is not about acquiring a specific technology, but about building a capability. The capability to make and enforce granular, evidence-based authorization decisions at enterprise scale. Therefore, the final prompt is this. Go back and look at your architecture diagrams. If they do not clearly articulate a system for computing trust from evidence, then you have more work to do. End the reliance on topology and implicit trust. Start building the decision engine. Treat zero trust not as a destination to be reached, but as a continuous cycle of decision-making that must be refined, hardened, and defended every single day. The security and resilience of your organization depend on it. If you found this helpful, imagine what you'll learn next. Join CyberTechHaus for weekly cybersecurity insights, tools, and breakthroughs. Hit subscribe now and stay ahead of every threat.